Okay, so I did do this once already, but with screen capture software, I promised, but then my screen capture software decided it's not going to work. So we're going to go the old-fashioned way with camera pointing at a screen. So, what I'm going to do here is I'm just going to start up the algorithm. I'm going to talk over it while we're doing stuff, because there's some other stuff. So, one advantage of now that we're not using screen capture software means I can point to things with my hand. So what we have over here is we have the Python console, start of evolution over here. I'm not sure if you can see that, but it says start of evolution, I promise, and that basically just tells me the algorithm has started. So what we have the algorithm doing is up here we have a function which is essentially just creating 1,000 random scrambles for ksolve according to certain subsets, and then it's putting them all in something called a text file called hi.txt because names are hard, and I'm just going to use, say, hi.txt, and it's doing all of those 1,000, and since this is a modified version of ksolve, I modified it so that it only outputs the average of those 1,000 scrambles. So although some of these subsets would be larger than 1,000 scrambles, 1,000 scrambles would be a reasonably good estimate for the average, I reckon. Most of them will be smaller. Well, not, I can't go far enough to say most. A lot of them will be smaller anyway. So yeah, that's basically what it does. So we see over here, we've evaluated the starting population, which is just 100 individuals, and it's given all of them a score. That's what all these averages are. And now it's doing the first generation. So it's taken those original 100, it's cross-mixed them, done all the genetic algorithmy stuff, and it's going to do generation 1, which it will spit out in a bit. While waiting for that, I'm going to go back and tell you why this is highlighting. It's highlighting because ksolve outputs C++ files. I'm working in Python, mostly because I'm good at Python, or I'm best at Python, and mostly because there's this thing called AutoHotkey, which just sends certain keystrokes to here. So this is just sending up. Control C, and then it's using my clipboard, if I can find where that is, here, converting it into a float, and yeah, essentially returning that as the score. If it doesn't find anything, it gives a score of 15. Normally that would be because it's too long, which if I ever go to 3x3 would actually be something that I'd use, but for now we're just staying here on 2x2 because 2x2 is easy, and I'm just going to use it as a proof of concept. So we have here generation 1 and generation 2 because I've been talking for too long, but we see that it gives all the stats. It gives the worst, the best, the average, and the standard deviation of each. So I'm going to read the digits out because you probably can't read them. First generation, the worst took 11.34 moves on average, the best took 10.37, and the average took 10.64 moves. Generation 2 took 10.8 as the worst, 10.32 as the best, and the average was 10.6. So you can see they're getting better. Again, trend continues. Generation 3, they just slowly keep getting better with every generation. It actually converges in about 15, I found, through various tests, but I did 25 for the other one just to be sure. So now that we've gone through that talk, I'm going to switch over and tell you about the Excel file and text file. Probably I'll probably put both in the description just to basically analyze that data. So I'm going to stop this. There we go, and we're going to move it over to the Excel spreadsheet. So the way I've got this formatted at the moment is that each genome just takes each what do you call them? Would they be DNA bases or would they be genes? Takes 1. So you can see my genome at the moment is a sequence of zeros and ones, specifically 14 zeros and ones. A 1 means not necessarily solved. It can be solved, but that is down to random chance. A 0 means always solved, always solved. Now, the first 40, so there are 14 because we have one corner, the down back left corner, fixed, and it's never going to move. We're only going to affect the others using R, U, and F moves. So what I have is the first 7. That wasn't 7, that's 7. These correspond to the permutation, and then the next 7 correspond to orientation. So essentially what that means is if you see a 1 here in a specific position, so say here, the first one would be up back left. A 1 here means that the up back left is not necessarily permuted. Here the up back right is not necessarily permuted, and so on. So these are the worst. I've actually sorted them roughly according to their scores, and yeah, this is the worst one. Hopeless product. It probably wouldn't make it to the next generation, but those aren't the ones that we're actually interested in. So we're going to have a look closer to the bottom, and I just realized I've not sorted it. Give me 5 seconds. Right, okay, we're back. I've actually sorted it now, mostly. There's still this weird one here, but yeah, ignore that. So here we have all of these, and we see the top 4 are actually more or less the same, and then the next few are also more or less the same. So this tells us there are in fact subsets which are better for solving than others on average in terms of optimal moves, obviously. So there are subsets which are which can be found using genetic algorithms which are faster optimally. So interestingly, I'll put a data dump so you can take a look down at the whole thing. I'll probably put this and this and the HTML version in the description, probably in Notepad and Excel forms. So see the scores here? None of them actually get quite below 10, but that doesn't matter. We just wanted to find the best ones, and the best ones, they all seem to have these 4, which basically means the U layer is permuted, interestingly. So if the U layer is permuted, but not necessarily oriented, apparently that gives us really the shortest optimal solutions on average in QTM. If you want to see me, a human who's not necessarily that good at 2x2, analysing how useful that subset is, then I'll put another, I'll put the other video that you can go watch up as well, probably at the same time. So, what can we learn from this? Well, this was a proof of concept, and I'm reasonably satisfied that the concept has been proven, that you can in fact use genetic algorithms and brute force solving to find subsets of the cube which are in fact shorter than others. There might be too many algorithms, the algorithm might be horrible, so those are 2 things we can look in further. I was considering training a version of AlgExplorer on the CubeSolves database, but unfortunately I can't work out how to download the CubeSolves database, so if anyone can help with that, it'd be much appreciated. Yeah, so that's it. Basic overview done. I'll put this down in the description, you can have a look through it if you want, and yeah, I'll see you guys sometime